In this lesson, we will learn about how to identify the types of intermolecular forces between molecules and also discuss some of the properties that can be compared using intermolecular forces. Now, first we must distinguish between intramolecular forces and intermolecular forces. Intramolecular forces are the forces within the molecules. So they're the ones that are holding atoms together in molecular compounds, the ionic bonds and the metallic bonds. So those hold those types of molecules or compounds together. The intermolecular forces are the forces between molecules. And there are three different types: London dispersion, dipole-dipole, and hydrogen bond that we will discuss. Ion-dipole forces will help us to explain some properties. Now, the order listed above, London dispersion, dipole-dipole, and hydrogen bonds, are the order of increasing intermolecular forces. So London forces are the weakest, and hydrogen bonds are the strongest of these three types of forces. Now, how we'll present them to you in the note is from the easiest to identify to a little bit more difficult to identify. And that's the progression that I've chose to present them to you. The first type of intermolecular force that we'll look at is the dipole-dipole force. And this occurs between two polar molecules. If you draw a molecule of CO, you'll see that there is a triple bond between the two atoms. There's a lone pair on the carbon and a lone pair on the oxygen. If you check the difference in electronegativity between these two atoms, you'll see that there is a polar bond between the two atoms, with the dipole pointed towards the oxygen because it is the more electronegative out of the two. Now, this is the molecule properly labeled with its dipole, but in order to look at intermolecular forces, we need to look at another carbon monoxide molecule beside it. So these are polar molecules, and where the intermolecular force lies is it's the force between the molecules holding them together in a sample. As you can see, the dipole on this molecule is slightly negative here, and on the neighboring molecule, it's slightly positive. So there's an attraction between the dipoles of the molecules, and that's where the intermolecular force lies. I'll use the short form IMF for intermolecular force, and this is a dipole-dipole attraction, or dipole-dipole force. Now, there are two diagrams here to show you how we might see these kinds of forces arising in a sample. This one on the right would represent a solid where the molecules are very orderly, and as you can see, they've aligned dipole to dipole to achieve maximum attraction and minimum repulsion. If you're looking at something like a liquid, the molecules will be a little bit less orderly, and there'll be a series of attractions from the negatives to the positives and repulsions from positive to positive or negative to negative. But overall, there are many intermolecular forces within the many molecules in a sample. We use a dashed line to represent our intermolecular forces because they aren't as permanent as a bond would be. When molecules in a liquid are moving around, for example, there are lots of intermolecular forces that are broken and new ones that are formed as the molecules move. Now, the hydrogen bond is the next type of intermolecular force that we'll look at, and it's the strongest of the three intermolecular forces. It's the most specialized as well. And there are two very specific requirements in order for us to be able to have a hydrogen bond between two molecules. The first thing that is needed is a slightly positive hydrogen atom. And this must come from a dipole. So there must be a polar bond within the molecule where hydrogen is left slightly positive. There also must be a lone pair of electrons on a neighboring atom. And that atom must be either oxygen, fluorine, or nitrogen. So let's look at an example here. We've got a water molecule. Water is bent with a lone pair. If I want to look at the intermolecular forces, I need to look at two different water molecules so I can examine the forces between the two. Now, what we have here, if we check the polarity of this bond, is we've got a slightly positive hydrogen atom. So there are dipoles, and I could draw dipoles on all four bonds. Let's check that we've got the requirements of a hydrogen bond. The intermolecular force occurs between a slightly positive hydrogen, so we've got that, and a lone pair of electrons on a neighboring oxygen, fluorine, or nitrogen. So what we have here is a slightly positive hydrogen, and that slightly positive hydrogen is going to be attracted to this lone pair of electrons on the oxygen. And that's where the intermolecular force will be. So the intermolecular force is between this lone pair and this dipole. Okay? And there are the possibility of two separate intermolecular forces because there are two lone pairs. Now, this type of intermolecular force is much stronger than the dipole-dipole force because rather than it being the attraction between a slightly positive to a slightly negative, as it is in a dipole, we've got a slightly positive to a negative from the lone pair of electrons in the oxygen. So therefore, this is a stronger attraction. Now, when we have hydrogen bonds, not only do we have the possibility of establishing this kind of an intermolecular force, the water molecule is still polar. So it is possible to also have dipole-dipole interactions between these two molecules, which again increases the overall intermolecular force. Let's look at NH3. Okay. NH3 is also tetrahedral. It ends up being pyramidal in its geometry because of the lone pair of electrons. And when we check the polarity of this bond, we see that hydrogen is slightly positive. So not only can we just look at this NH3 and say it's a polar molecule because of the lone pair, so it probably has dipole-dipole, we want to look even further to check whether or not hydrogen bonding is possible, because we know that hydrogen bonds are even stronger than the dipole-dipole forces. So what we have here is a slightly positive hydrogen, and we've got a lone pair on a neighboring nitrogen. So the attraction is going to be to the hydrogen, and that's where the hydrogen bonds are going to be. Now, the strength of these hydrogen bonds has actually led scientists to redefine hydrogen bond, because most intermolecular forces are thought of as being non-permanent and quite weak, but the hydrogen bond, as it's studied further, is showing that it actually does have significant overlap between the orbitals of the molecules, and it is much more like a covalent bond than other intermolecular forces. Now, the two types of intermolecular forces that we've talked about so far, the dipole-dipole and the hydrogen, have applied to polar molecules. The third type of intermolecular force, which is London dispersion forces, applies to nonpolar molecules. Now, all molecules will be able to exhibit this type of force, London forces. However, for nonpolar molecules, it is the only type of intermolecular force that they will be able to exhibit. And these are pretty weak. Now, what we have to remember is that we've got a nonpolar molecule. So if I were to look at this molecule, there's no charge separation. So there's no slightly positive side or slightly negative side like there would be in a nonpolar molecule. What can happen, though, is through polarization, we can form an instantaneous dipole. An instantaneous dipole is formed because the electrons within the orbitals in the molecule are randomly moving around. And it's possible that for a moment in time, enough electrons will gather in one area to leave one part of the molecule slightly negative. That will leave another part of the molecule slightly positive. The effect on a neighboring molecule is that the electrons in this molecule will repel these electrons, and so we'll end up with a similar charge separation where we've got a slightly positive and a slightly negative end of the molecule. The formation of these instantaneous dipoles will lead to the possibility of an attraction between the two molecules. And this attraction is the London force. Now this intermolecular force is quite weak because as quickly as it's formed, it's going to be broken. As quickly as these electrons end up in one area leading to this charge separation, they're going to repel one another and as a result break the intermolecular force. So these are referred to as instantaneous dipoles. And also sometimes they are called momentary dipoles. And that's what this is here. This is the momentary or the instantaneous dipole. Now, in order to decide what type of intermolecular forces will be exhibited between molecules, you first need to draw the three-dimensional structure and decide the polarity of the molecule. Once you've got that, you can decide if hydrogen bonding is possible by deciding if it meets the very strict requirements of having a slightly positive hydrogen and a lone pair on either nitrogen, oxygen, or fluorine. If it can exhibit hydrogen bonds, then you know that all three types of intermolecular forces are possible. So if you're asked for a list, you would list all three. If you're simply discussing the intermolecular forces of a variety of molecules for point of comparison, and one of them exhibits hydrogen bonds, you could just discuss the fact that it has hydrogen bonds, because it is known that if it has hydrogen, it has the other three. If hydrogen bonds are not possible, you would then look at whether the molecule is polar or nonpolar. If the molecule is polar, it will exhibit dipole-dipole and London forces. If it's nonpolar, then London forces are the only intermolecular force that is possible. Now that we're able to identify the intermolecular forces of molecules, we can go back to the very first chart that we looked at the beginning of the unit. The starter of our unit compared the properties of ionic and molecular compounds. And at that point, we discussed the fact that molecular compounds had some lack of clarity in terms of their properties. For example, we said that they could be solids, liquids, or gases. And we said that they could have low solubility or no solubility. So it was showing us that there is some differentiation needed among molecular compounds. And our discussion through the molecules has given rise to these two families of molecules, polar and nonpolar molecules. So now we essentially have three main major types of molecules. We've got ionic compounds, we've got polar, and we've got nonpolar compounds. And their properties are a result of some of the intermolecular forces that they have, or the properties that they have being ionic with the positive and negative ions. So first of all, for the state, ionic compounds tend to be crystalline solids. As you know, the ions within ionic compounds are organized in a very rigid manner in a crystal lattice, giving rise to their crystalline nature and their ability to reflect light in the way that they do. Molecular compounds that are polar tend to be liquids and solids. They tend to have hydrogen bonds and dipole-dipole forces that are able to hold them together in liquid or solid states. For nonpolar molecules, because they can only exhibit London forces, they tend to be gases because their intermolecular forces tend to be quite weak and their molecules are not held very closely together. For the electrical conductivity, ionic compounds are able to conduct electricity as a liquid in their molten state or when they're dissolved in water because they have ions present. Both polar and nonpolar molecules do not allow for the conduction of electricity. Let's look at the melting point and the solubility next. When we're talking about solubility in water, there's a phrase that we use that is like dissolves like. So water, being a polar molecule, tends to dissolve other polar molecules and will also tend to dissolve ionic compounds because of its ability to have an ion-dipole interaction between the water molecule and the ions in an ionic compound. When you think of solubility, what you want to think about is the fact that if something is dissolved, it's essentially being surrounded by the solute. So if water is able to surround a particular solute, then it will be able to dissolve it. And in order to surround it, it needs to be able to interact with it in a positive way. So when we look at ionic compounds, so for example, if we have something like sodium chloride dissolving, what essentially happens is the sodium chloride is dissolved by breaking up into its ions. And what happens is the water molecules will surround the positive ions and surround the negative ions. And the way that it surrounds it is something like this, a three-dimensional picture. So this ion in the center here has a positive charge, and so that's why the water molecules are all pointing with the oxygen facing this positively charged ion, because that's the most positive ion-dipole interaction. If it were chlorine in the center here that was being dissolved by the water molecules would be facing the other direction because there would be a stronger attraction between the negative ions and the positive side of the water molecules, which is the side with hydrogen. Right? So we're getting this from the fact that water molecule looks like this. Its overall dipole goes through the middle. So the oxygen is the negative end of the water molecule, and the hydrogen is the slightly positive end of the molecule. Now on this side, they're showing you that the sodium ion, which has a positive 1 charge, is going to have a weaker interaction to the water molecule than this smaller magnesium with a positive 2 charge. Okay, so that's just something to note as we discuss solubility later on in the year. Now if you have a polar molecule, that means that it's got a slightly positive end and a slightly negative end. And so many polar molecules will be soluble in water because water can effectively interact with and surround the polar molecule. We use a little representation like this for our water molecule, whereby the pointed end is the oxygen and the other end are the hydrogens. We can see that water would surround this polar molecule in this fashion. where the oxygens would point towards the slightly positive end and the hydrogens would point towards the slightly negative end. Overall, the idea is that polar molecules are able to dissolve because water is able to interact with them. A nonpolar molecule that has no slightly positive or slightly negative end will not be able to effectively dissolve because water cannot effectively interact with it. If we want to discuss the boiling point and melting point of different molecules, it's important to understand the difference between a solid, a liquid, and a gas at the molecular level. And as you know from your studies of these phases of matter, there are more interactions between the molecules in a solid versus a liquid versus a gas. And if you want to melt something, you're going to go from a solid to a liquid. And if you want to boil something, you're going to go from a liquid to a gas. Now, what's really important in your discussion of these properties of melting and boiling is that you express the fact that when you want to melt something, you need to break intermolecular forces. So in order to change a solid to a liquid, I need to spread the molecules apart. And so in order to do that, I need to break intermolecular forces. The same thing will happen going from a liquid to a gas. I need to break intermolecular forces in order to spread these molecules apart. So therefore, in our discussion of melting and boiling points, in order to compare them, the higher the intermolecular forces, the greater the boiling point or the melting point. Because we will need more energy in order to break those intermolecular forces. So a higher temperature is needed. So if you're asked to compare the boiling point or the melting point of two different substances, what you want to do is identify what type of intermolecular forces are present. It might be obvious from the type of intermolecular forces right away which one has the higher melting or boiling point. If both compounds have the same type of intermolecular force, so for example, they're both nonpolar with London forces, then you would look to the number of electrons to help you to compare the number of intermolecular forces that might be possible. So for something with more electrons, they're going to be more polarizable. There's going to have greater intermolecular forces, and therefore the higher boiling or melting point. This graph here gives a nice comparison of boiling points of the hydrogen compounds of elements in the same group. And we can see some very specific applications of the types of intermolecular forces within the compounds. First, let's look at this group here. So you can see that these are all the hydrides of the compounds in group 4. So they're going to have a similar structure. These are all going to be tetrahedral molecules. And what you can see is as we go down the group, we increase the boiling point relatively steadily. Now, if you examine these, you'll see that they're all tetrahedral, so they're all going to be nonpolar molecules. So the type of intermolecular forces that CH4, SiH4, GeH4, and SnH4 will exhibit are London forces. So the explanation for the natural increase in boiling point as we go down the group is related to the number of electrons. We're increasing the number of electrons in the compounds, so we're increasing the polarizability and therefore the amount of London forces, and in turn the boiling point. Now, for all of the other groups, we see that there is not the same natural increase as we go down the group. We would expect, if it followed the same pattern, that H2O, for example, would have a boiling point somewhere around here, and it would just naturally increase. And the same for HF, we would expect it to be lower than HCl, and we would expect it to increase as we went down the group. Let's compare these molecules. For the rest of these molecules, NH3, H2O, and HF, we are dealing with families of molecules that are all polar. The group with NH3 are pyramidal, HF are just small diatomic molecules, and H2O and its family are bent. Okay, but with the lone pairs, they all end up being polar molecules. So all of them can exhibit dipole-dipole interactions, which nicely explains why the entire set of them is higher than the group for A hydrides. Because they are all polar molecules, they're all going to have the ability to form dipole-dipole forces. What's different about H2O, HF, and NH3, which leads them to have a significantly higher boiling point than any of the other compounds in their same group, is the fact that they can exhibit hydrogen bonds. So NH3, HF, and H2O can exhibit hydrogen bonds, and that's why their boiling points are so much higher than the other compounds in the group. The other compounds in the group, for example, these ones, all can exhibit dipole-dipole forces, and it increases as we go down the group because of the increase in the number of electrons and the increase in the polarizability. So this is a really nice graph because it helps us to examine the property of boiling point among the hydrides and very nicely shows the effect of the different types of intermolecular forces and the effect of the number of electrons and polarizability.